There's a crisis brewing in cosmology. And I don't mean the kind of crisis where scientists are mildly concerned and need to run a few more experiments. I mean the kind of crisis where the fundamental measurements we use to understand the entire universe are giving us contradictory answers, and nobody can figure out why. At the center of this crisis is a deceptively simple question. How fast is the universe expanding? You'd think we'd have this figured out by now. We've measured cosmic expansion for nearly a century. We've launched telescopes into space. We've observed distant supernova, mapped the cosmic microwave background, and cataloged billions of galaxies. We have more data about the universe than ever before. And yet, when different teams of scientists measure the expansion rate using different methods, they get different answers. Not slightly different, significantly different. Different enough that it can't be explained by measurement errors or bad luck. This discrepancy has a name, the Hubble tension, and it's forcing physicists to consider some truly wild possibilities about the nature of reality. One of the most intriguing explanations is that we might be living inside a massive cosmic void, a region of space where matter is less dense than the rest of the universe. If this is true, it would mean that our view of cosmic expansion has been skewed by our local environment. We've been measuring the universe from inside a bubble, and we didn't even know it. But here's where it gets really interesting. If we are in a cosmic void, it could solve the Hubble tension. Different measurements would give different results because they're measuring expansion in fundamentally different regions of space. Or it might not solve anything. It might just add another layer of complexity to a problem that's already making cosmologists lose sleep. Today, we're going to dive deep into this mystery. We'll explore what the Hubble tension actually is, why it matters, and whether the idea of a cosmic void can save us from rewriting fundamental physics. We'll look at the evidence, the arguments, and the implications of living in a universe that might be more complicated than we ever imagined. This is the story of how a small discrepancy in cosmic measurements has turned into one of the biggest mysteries in modern physics. And it all starts with a number that astronomers can't agree on. Let's begin. Part 1. The Hubble constant and why it matters. Chapter 1. What is the Hubble constant? Before we can understand the crisis, we need to understand what we're actually measuring. The Hubble constant, usually written as h0, is the rate at which the universe is expanding right now. Edwin Hubble discovered in 1929 that distant galaxies are moving away from us. And the farther away they are, the faster they're receding. This relationship is remarkably simple. Velocity equals the Hubble constant times distance. If a UHT in a galaxy is twice as far away, it's moving away from us twice as fast. This discovery revolutionized our understanding of the universe. It meant the cosmos wasn't static and eternal, as Einstein and others had believed. It was expanding, which implied it had a beginning, what we now call the Big Bang. The Hubble constant is measured in units of kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. So if the Hubble constant is 70 kilometers per second per megaparsec, it means that for every megaparsec of distance, galaxies are moving away from us 70 kilometers per second faster. Why does this number matter so much? Because it's fundamental to almost everything we know about cosmology. The Hubble constant tells us the age of the universe. A faster expansion rate means the universe reached its current size more quickly, making it younger. A slower rate means it's older. The size and scale of cosmic structures. Understanding expansion helps us figure out how galaxies, clusters, and other structures formed and evolved. The nature of dark energy. The expansion rate affects our calculations about the mysterious force causing the universe to expand faster over time. Distances to far-off objects. We use the Hubble constant to calculate how far away distant galaxies are. Get this number wrong, and our entire cosmological model starts to crumble. Every calculation, every prediction, every understanding of cosmic history depends on knowing H0 accurately. For decades, astronomers worked to pin down this number with increasing precision. In the 1990s and early 2000s, different measurement methods were converging on similar values. It looked like we were closing in on the answer. Then something strange happened. As measurements got more precise, instead of agreeing more closely, they started diverging. The better our data got, the more contradictory our results became. That's not supposed to happen in science. Chapter 2. The 2 ways to measure cosmic expansion. The Hubble tension exists because we have 2 fundamentally different ways of measuring the expansion rate, and they're giving us different answers. Let's call these the early universe method and the late universe method. The early universe method, the cosmic microwave background. The cosmic microwave background, or CMB, is the afterglow of the Big Bang. About 380,000 years after the universe began, it had cooled enough for atoms to form. Before this, the universe was so hot that light couldn't travel freely. It would immediately hit a charged particle and scatter. But once atoms formed, light could suddenly travel across the cosmos unimpeded. That light has been traveling toward us ever since. It's now stretched by cosmic expansion into microwave radiation, forming a nearly uniform glow in every direction we look. The ESA's Planck satellite mapped this radiation with extraordinary precision from 2009 to 2013. The map shows tiny temperature fluctuations, regions that were slightly denser or less dense in the early universe. These fluctuations eventually became the galaxies and cosmic structures we see today. But here's the key. The pattern of these fluctuations is determined by the fundamental properties of the universe, including the expansion rate. By analyzing the CMB in exquisite detail, physicists can extract a value for the Hubble constant. The Planck team's result? H0 equals 67.4 kilometers per second per megaparsec, with an uncertainty of less than 1%. This is an indirect measurement. We're not watching galaxies move. We're looking at the baby universe and using our model of cosmic evolution to infer what the expansion rate should be today. The late universe method, the cosmic distance ladder. The other approach measures the expansion rate directly by observing how fast galaxies are moving away from us right now. But there's a problem. To calculate expansion rate, we need to know both how fast galaxies are moving and how far away they are. We can measure velocity easily using redshift, the stretching of light from moving objects. But measuring cosmic distances is much harder. This is where the cosmic distance ladder comes in. It's a series of measurement techniques, each building on the previous one allowing us to measure distances to increasingly distant objects. Rung 1, parallax. For the nearest stars, we use parallax, the apparent shift in position as Earth orbits the Sun. This gives us direct geometric distances, no assumptions needed. Rung 2, Cepheid variables. Cepheid stars pulse with a period that's directly related to their intrinsic brightness. By measuring how long it takes them to pulsate, we know how bright they actually are. Comparing this to how bright they appear tells us how far away they are. We calibrate cepheids using parallax measurements to nearby cepheids, then use them to measure distances to galaxies millions of light years away. Rung 3, Type 1, a supernova. These stellar explosions are remarkably consistent in brightness, making them standard candles, visible across billions of light years. We calibrate them using galaxies where we've measured distances with cepheids, then use them to measure the expansion rate across cosmic distances. Adam Rees and his team at Johns Hopkins have spent years perfecting this technique. Their latest result, published in 2024, H0 equals 73.2 kilometers per second per megaparsec, with an uncertainty of about 1%. This is a direct, local measurement. We're watching the universe expand in our cosmic neighborhood and measuring it directly. The problem 67.4 versus 73.2? That's a 9% difference. It might not sound like much, but in cosmology, it's enormous. Both measurements are extremely precise. Both teams have checked and rechecked their work. Both methods are based on solid physics. And yet, they disagree by far more than their stated uncertainties. If we trust the CMB measurement, the universe is about 13.8 billion years old and expanding at a particular rate described by the standard cosmological model. If we trust the local measurement, the universe is younger, maybe 12.8 billion years old, and something is wrong with our cosmological model. They can't both be right. Chapter 3: Why this isn't just a measurement error. When scientists first noticed the Hubble tension around 2013, the initial reaction was basically, that's weird. But our measurements will probably converge as we get better data. That's not what happened. As both teams improved their measurements and reduced uncertainties, the discrepancy didn't shrink. It grew. The more carefully we measured, the more certain we became that the two methods were giving genuinely different answers. Let's be clear about what this means. These aren't sloppy measurements. Both teams have done exhaustive checks. The Planck team checked for instrumental errors. None found that could explain the discrepancy. Verified their theoretical model. It matches a huge range of other observations. Considered foreground contamination from our galaxy, accounted for and minimal. Tested alternative analysis methods. Results remain consistent. The SH0ES team, Rees's group, recalibrated the distance ladder using multiple independent methods. Results agree. Used different types of cepheids, same answer. Checked for systematic errors in supernova observations. None found. Got confirmation from independent teams using similar methods. They agree. Multiple independent teams using completely different measurement techniques get results consistent with one side or the other. Supporting the low value, approximately 67. Planck satellite CMB measurements, ACT, Atacama Cosmology Telescope, CMB measurements. Some methods using gravitational lensing. Some methods using baryon acoustic oscillations, supporting the high value, approximately 73. SH0ES distance ladder measurements. Measurements using tip of the red giant branch stars. Some megamaser distance measurements. Some strong lensing measurements. The tension has been confirmed by so many independent methods that it's extremely unlikely to be a simple error. The statistical significance is now over 5 sigma. In particle physics, that's the threshold for claiming a discovery. Something real is going on here. Chapter 4. What could explain the discrepancy? When your most precise measurements contradict each other, you have 3 options. Option 1. One measurement is wrong. Maybe despite all the checks, there's a subtle systematic error in one method that everyone has missed. The problem? Both methods have been verified by independent teams using different approaches. Finding a hidden error that affects all of them the same way seems increasingly unlikely. Option 2. Our cosmological model is wrong. Maybe the lambda CDM model, our standard model of cosmology, is missing something important. Lambda CDM assumes general relativity is correct. The universe contains dark matter, which we can't see but detect through gravity. The universe contains dark energy, causing accelerated expansion. The universe is homogeneous and isotropic, same in all directions. What if one of these assumptions is wrong? What if there's new physics we haven't discovered yet? Option 3. Both measurements are right, but they're measuring different things. This is the really interesting possibility. What if the universe is more complicated than our model assumes? What if cosmic expansion isn't perfectly uniform? What if our local environment is different from the universe as a whole? This is where the cosmic void hypothesis comes in. Part 2. The local void hypothesis. Chapter 5. What is a cosmic void? Before we ask whether we live in one, we need to understand what cosmic voids actually are. When you look at the large-scale structure of the universe, it's not uniform. Galaxies aren't scattered randomly through space. They're organized into an enormous cosmic web, filaments, long chains of galaxies stretching across hundreds of millions of light years. Walls, vast sheets of galaxies, clusters, dense concentrations where filaments intersect. Voids, vast regions with very few galaxies. The voids are huge. We're talking about regions 100 to 400 million light years across that contain very few galaxies compared to the cosmic average. They're not completely empty. There are some small galaxies in there, but they're underdense by 20% to 90% compared to the mean density of the universe. Think of the cosmic web like soap bubbles. The galaxies are concentrated in the thin films between bubbles. The voids are the empty spaces inside the bubbles. These structures formed from tiny density variations in the early universe. Slightly denser regions attracted more matter through gravity, becoming denser still. Slightly less dense regions lost matter to their denser surroundings, becoming voids. We've mapped thousands of these voids. They're a fundamental feature of cosmic structure. No controversy there. The controversial question is, could we be living inside an unusually large underdense region? And if so, could that explain the Hubble tension? Chapter 6. The local void hypothesis. Here's the basic idea. If we're located in a region where matter density is lower than the cosmic average, space in our region might be expanding at a different rate than space in denser regions. Think about it this way. The expansion of space is driven by the battle between the outward push of dark energy and the inward pull of gravity from matter. In an underdense region with less matter, there's less gravitational pull to slow expansion. So space might expand slightly faster in a void than in denser regions. Now, here's where it gets relevant to the Hubble tension. The CMB measurement looks at the entire observable universe. It's measuring cosmic expansion averaged over the largest scales. It doesn't care about local variations because it's averaging over everything. The local measurement looks at galaxies relatively near us, within a few 100 million light-years. If we're in a void, this measurement would be biased toward the faster expansion rate in our local underdense environment. So both measurements could be correct. They're just measuring expansion in different density environments. The early universe measurement gives us the expansion rate for the universe as a whole, 67.4 kilometers per second per megaparsec. The local measurement gives us the expansion rate in our underdense region, 73.2 kilometers per second per megaparsec. If this is correct, it would solve the Hubble tension without requiring new physics or throwing out our cosmological model. We just need to account for the fact that we're not in an average location. Chapter 7. The Keenan-Barger-Cowie supervoid. The idea that we might live in a large void isn't new. In 2013, astronomers Ryan, Keenan, Amy Barger, and Lennox Cowie published a paper identifying what they called a supervoid in our cosmic neighborhood. They analyzed the distribution of galaxies within about 1 billion light-years of us and found something striking. There's a region about 1 to 2 billion light-years across where galaxy density is lower than the cosmic average. The KBC Void, as it's called, has its center somewhere between us and the constellation Boötes. According to their analysis, we're not at the center of this void, but we're somewhere inside it, maybe a few 100 million light-years from the edge. The void isn't dramatically underdense, maybe 20 to 30% less dense than average in most regions. But it's large, really large. One of the largest underdense structures known. If this void exists as described, and if voids genuinely affect local expansion rates, it could potentially explain the Hubble tension. But there are problems. Chapter 8. The problems with the void hypothesis. The cosmic void solution sounds elegant, but it faces several serious challenges. Problem 1. How underdense does it need to be? To fully explain the Hubble tension, the void would need to be pretty severely underdense, maybe 50% or more below the cosmic average in some models. But observations of galaxy distributions suggest our local region is only about 20 to 30% underdense at most. Some studies find even less of a deficit. That might not be enough to explain a 9% difference in expansion rates. Problem 2. How big does it need to be? For the void to affect our measurements of the Hubble constant, it needs to be larger than the distances to the objects we're using to measure expansion. The SH0ES team measures Hubble constant using supernova out to several 100 million light-years. The void would need to extend significantly beyond this. Some models suggest we'd need a void 3 to 4 billion light-years across to fully explain the tension. That's enormous, larger than Milky most voids we've identified, and if the void is that large, we should see its effects in other ways. More on that shortly. Problem 3. Are we in a special location? The Copernican principle, the idea that we don't occupy a special place in the universe, has been a guiding principle in cosmology for centuries. If we happen to be located in an unusually large, unusually underdense region that just happens to create a measurement discrepancy that looks like new physics, that's a pretty special location. It's not impossible. Random chance means someone has to be in the unusual locations. But it does require us to be cosmically unlucky, or lucky, depending on your perspective. Problem 4. The CMB should show evidence of the void. If we're in a very large void, it should affect the cosmic microwave background in detectable ways. Light from the CMB passes through the void on its way to us. In an underdense region, the gravitational potential is different than in denser regions. This affects the light's energy through something called the integrated Sachs-Wolf effect. We should see a specific pattern in the CMB, a cold spot in the direction of the void's center, where photons lost energy climbing out of the gravitational potential well. Some studies claim to see hints of this. Others find no significant evidence. The jury is still out, but if we're in a void large enough to explain the Hubble tension, the effect on the CMB should be pretty clear. And it's not. Problem 5. Alternative distance measurements. The distance ladder isn't the only way to measure local expansion. Other methods include gravitational lensing time delays, tip of the red giant branch stars, Moser distances, surface brightness fluctuations. Some of these methods also give high values around 73, supporting the SH0ES result. If the void hypothesis is correct, all these methods would need to be equally biased by our local environment. That's possible, but it requires the void to have a very specific structure that affects all these different measurements in just the right way. Chapter 9. Recent evidence for and against the void. Hypothesis has been hotly debated over the past few years. Let's look at some key recent studies. Evidence supporting the void. A 2024 paper by Mockdad and colleagues analyzed galaxy distributions using improved datasets and found evidence for a significant underdensity extending to about 1 billion light-years, with us near the center. They calculated that this could account for about 2 to 3 kilometers per second per megaparsec of the Hubble tension. Not all of it, but a meaningful fraction. Another study by Keenan, one of the original KBC Void discoverers, updated their analysis with newer data and confirmed that the underdensity persists. They argued that while it might not explain the entire tension, it's a real feature that needs to be accounted for. Some gravitational lensing studies have found hints that the local expansion rate does vary with direction, which could be consistent with void effects. Evidence against the void. A major 2023 study by Sheth and colleagues analyzed multiple galaxy surveys and found that while local underdensities exist, they're not nearly large or severe enough to explain the Hubble tension. They calculated that the maximum effect on H0 from local structure would be about 1 to 2 kilometers per second per megaparsec. Significant, but not enough to close the gap. Multiple analyses of the CMB have found no evidence for the large-scale void signature you'd expect if we were in a supervoid large enough to explain the tension. A 2024 paper by Kenworthy and colleagues used kinematic measurements, how galaxies are actually moving, not just receding from expansion, to map the local density field. They found inhomogeneities, but nothing dramatic enough to account for the discrepancy. The Dark Energy Survey team analyzed their massive dataset of hundreds of millions of galaxies and concluded that local structure is not unusual enough to solve the Hubble tension. The current consensus. Most cosmologists now think that while we probably are in a somewhat underdense region, it's not extreme enough to fully explain the Hubble tension. At best, it might account for 20 to 30% of the discrepancy. That means we still need another explanation for the remaining gap. Part 3: Alternative Explanations and Implications. Chapter 10: New Physics Options. If the void hypothesis doesn't fully solve the problem, what else could explain the Hubble tension? Physicists have proposed numerous modifications to our cosmological model. Early dark energy. What if dark energy wasn't constant throughout cosmic history? What if there was a burst of extra dark energy in the early universe that affected the CMB but not local measurements? This would make the early universe expand faster than expected, which would be encoded in the CMB. But it wouldn't affect current local measurements, potentially reconciling the two values. The problem? We have no evidence for early dark energy from any other observations. It's an ad hoc solution created specifically to solve this problem. Modified gravity. What if Einstein's general relativity isn't quite right on cosmic scales? What if gravity behaves slightly differently than we think? Some modified gravity theories predict different expansion histories that could affect the CMB measurement without changing local dynamics. The problem? General relativity has passed every test we've thrown at it with flying colors. Modifying it just to solve one discrepancy while keeping all its other successes is extremely difficult. Extra radiation. What if the early universe contained more radiation than our standard model predicts? This would change how the CMB formed and affect the inferred expansion rate. The problem? We have tight constraints on the amount of radiation in the early universe from multiple observations. There's not much room for extra radiation without conflicting with other data. Varying fundamental constants. What if the fundamental constants of nature, things like the speed of light or the gravitational constant, were slightly different in the early universe than they are now? The problem? This is a radical proposal with far-reaching consequences. If fundamental constants change, it affects everything. Making it work with all our other observations is nearly impossible. Primordial magnetic fields. Some theorists have proposed that strong magnetic fields in the early universe could affect how we interpret the CMB, changing the inferred Hubble constant. The problem? We have no evidence for such magnetic fields, and generating them requires new physics in the very early universe. Interacting dark matter and dark energy. What if dark matter and dark energy interact with each other in ways we haven't accounted for? The problem? We have no evidence for such interactions, and it's unclear how to construct a model that solves the Hubble tension without creating new problems. All of these proposals face the same fundamental challenge. They're invented specifically to solve the Hubble tension, but they don't have independent evidence supporting them. They're theoretical band-aids, not robust explanations. Chapter 11: Measurement Systematics. could we still be missing something? Despite years of checking, some physicists still think there might be a subtle systematic error that everyone has overlooked. Distance ladder systematics. The cosmic distance ladder depends on calibrating each rung using the previous one. Errors can compound. Cepheid metallicity. Cepheid pulsation periods depend on their chemical composition. If we're not accounting for this correctly, our distance measurements could be systematically off. The SH0ES team has checked this extensively. They find that metallicity effects are small and well understood, but some critics argue there could be subtler effects we're missing. Cepheid crowding. In distant galaxies, multiple stars can blend together in our images. If bright Cepheids are systematically blended with other stars, we might think they're brighter than they actually are, leading us to think they're closer than they really are. Again, the SH0ES team has checked this using high-resolution Hubble images. They find minimal crowding effects. But is it possible there's something subtle still being missed? Supernova systematics. Type 1. A supernova aren't perfectly standard candles. There's intrinsic variation in their brightness. We correct for this using empirical relationships, but what if these relationships don't hold exactly at large distances? Multiple teams have checked this. The corrections seem robust, but could there be evolution in supernova properties over cosmic time that we're not accounting for? CMB systematics. The CMB measurement also involves systematic uncertainties. Foreground contamination. Our galaxy emits radiation that contaminates the CMB signal. The Planck team carefully modeled and subtracted this, but could there be residual contamination? Multiple independent analyses using different foreground models get consistent results, suggesting this isn't the issue. Instrumental effects. Could there be uncorrected instrumental systematics in the Planck data? The Planck team did exhaustive checks. Independent analyses of data from other CMB experiments, like ACT and SPT, get consistent results, suggesting instrumental effects aren't the problem. Theoretical modeling. The CMB measurement depends on our theoretical model of the early universe. What if something in that model is wrong? This is more plausible, but it would require errors in very well-tested physics, and it would likely show up in other observations beyond just the Hubble constant. The verdict. After years of scrutiny, most experts think systematic errors are unlikely to fully explain the tension. Both measurements have been checked too many times by too many independent groups. But science is humble. It's possible, though increasingly unlikely, that there's some subtle effect everyone has missed. Part 4. Deeper into the Void. The Physics and Observations. Chapter 12. How voids actually affect expansion. To really understand whether a void could solve the Hubble tension, we need to dig into the physics of how underdense regions affect cosmic expansion. The expansion of space isn't driven by galaxies flying apart through pre-existing space. Space itself is expanding, carrying galaxies along with it. The rate of this expansion depends on the energy content of space, both matter, which gravitationally resists expansion, and dark energy, which drives accelerated expansion. In a perfectly homogeneous universe, expansion would be the same everywhere. But our universe isn't perfectly homogeneous. It has structure, dense regions and underdense regions. The physics of voids. In an underdense region, there's less matter pulling back against expansion. You might think this would make the void expand faster, but it's more complicated than that. When a void forms, matter flows outward from its center toward the denser regions surrounding it. This creates a peculiar velocity field. Galaxies have motion in addition to the Hubble flow. The expansion rate inside a void depends on several factors. The void's density profile. How much less dense is the center compared to the edges? A void that's 20% underdense has different effects than one that's 80% underdense. The void's size. Larger voids have had more time for matter to evacuate from their centers, potentially creating more extreme underdensities. The void's age. Younger voids are still actively forming, with matter still flowing outward. Older voids have reached a more stable configuration. Cosmological context. The expansion of a void is also affected by the large-scale expansion of the universe and the properties of dark energy. The mathematical framework. Physicists use several approaches to calculate void effects. Perturbation theory treats the void as a small perturbation on top of the smooth cosmic expansion. This works for small, mildly underdense voids, but breaks down for larger, emptier voids. N-body simulations, computer simulations that track the gravitational interactions of millions of particles as cosmic structure forms. These can model complex void dynamics, but require assumptions about cosmological parameters. LTB models, Lemaitre-Tolman bondi. Solutions to Einstein's equations describe spherically symmetric inhomogeneous universes. These exact solutions allow us to model what happens if we're at the center of a large spherical void. The LTB approach is particularly relevant to the Hubble tension because it can calculate precisely how being in a void would affect our measurements. What the calculations show. Multiple groups have run these calculations, and they consistently find, to explain the full 9% Hubble tension with a void, you need a void radius of at least 1 to 2 billion light-years, an underdensity of 30 to 50% in the void's central region. Us located within a few hundred million light-years of the center, these aren't impossible requirements, but they're extreme. We'd need to be in one of the largest, most underdense structures in the observable universe. Moreover, such a large void would have observable consequences beyond just the Hubble tension. Chapter 13. The Smoking Gun Observations. We should see. If we're in a supervoid large enough to explain the Hubble tension, it should leave multiple observable signatures. Let's examine what we should see and whether we actually see it. Signature 1. The CMB cold spot light from the cosmic microwave background travels through the void to reach us. As it enters the void, photons fall into a gravitational potential well and gain energy, blue shift. As they climb out on the other side, they lose energy, red shift. In a static void, these effects would cancel out, but the universe is expanding. The void's gravitational potential is changing as the universe evolves. This creates a net effect called the integrated Sachs-Wolf ISW effect. For a large void, we should see a cold spot in the CMB, a region where the temperature is slightly lower than average, aligned with the void's location. What we observe. The CMB does contain cold spots, most famously, the CMB cold spot, discovered in 2004. It's located in the direction of the constellation Eridanus, and it's about 10 microkelvins colder than average. Could this be our supervoid? Several studies have investigated, 2015 study by Sapudi and colleagues found a large supervoid in the direction of the cold spot, spanning about 1.8 billion light years. They proposed it could partially explain the cold spot. However, other studies found that the void isn't quite large or underdense enough to fully explain the temperature deficit. And the cold spot's statistical significance is debated. It might just be a rare but not impossible random fluctuation. More importantly, if the KBC void, the one potentially causing the Hubble tension, exists, we should see a cold spot in the direction of Boötis, not Eridanus. Some studies claim to find a smaller temperature decrement in that direction, but it's not as prominent as the Eridanus cold spot. Verdict: the CMB evidence is ambiguous. We see some cold spots, but they don't clearly match what we'd expect from a supervoid large enough to solve the Hubble tension. Signature 2, anisotropic expansion. If we're in a large void, the expansion rate shouldn't be the same in all directions. Looking toward the void's center, where density is lowest, we should measure faster expansion. Looking toward the edges or beyond, we should measure slower expansion. This would violate the cosmological principle, the assumption that the universe looks the same in all directions, but only on scales smaller than the void. What we observe? Several groups have looked for directional variations in the Hubble constant. A 2020 study by Collin and colleagues analyzed Type 1 supernovae and found hints of anisotropy. The expansion rate seemed slightly higher in some directions than others. They suggested this could be evidence for void effects. However, a 2021 study by Mohayyai and colleagues analyzed the same data differently and found no significant anisotropy beyond what you'd expect from random chance. A 2023 study using strong gravitational lensing also looked for directional variations and found maybe. The results were marginal, with barely significant hints of anisotropy that could go away with more data. Verdict: some studies find marginal evidence for anisotropic expansion, but it's not robust. More data is needed. Signature 3, peculiar velocity flows. If we're in a large void, galaxies should show bulk flow motions, systematic patterns in how they're moving, beyond just Hubble expansion. Near the void's edge, galaxies should be flowing outward away from the underdense center. From our perspective inside the void, we should see this as a pattern of peculiar velocities. What we observe? Large-scale peculiar velocity surveys have been conducted, most notably. The Cosmic Flows project has measured distances and peculiar velocities for thousands of galaxies out to several hundred million light-years. The 6DF Galaxy Survey measured peculiar velocities for thousands of galaxies in the southern hemisphere. What do they find? There are indeed large-scale flows, but they're complex. Some studies claim to see patterns consistent with void outflows. Others interpret the same data as showing infall toward dense structures like the Shapley supercluster. A 2024 analysis by Watkins and colleagues synthesized multiple velocity surveys and found that while local flows exist, they're not obviously organized around a giant void centered near us. Verdict: the peculiar velocity data doesn't clearly support or refute the supervoid hypothesis. The flows are complex and can be interpreted multiple ways. Signature 4, galaxy density gradients. This is the most direct test. Just count galaxies at different distances in different directions. If we're in a supervoid, we should see fewer galaxies nearby, we're in the underdense region, galaxy density increasing as we look farther out, approaching the void's edge, asymmetry, more galaxies in some directions than others. What we observe. This is where the evidence gets interesting and complicated. The Keenan-Barger-Cowie 2013 paper that identified the KBC supervoid used galaxy counts from the SDSS survey. They found that galaxy density is indeed lower nearby and increases with distance, exactly as you'd expect if we're in a void. However, subsequent studies with more complete surveys found different results. A 2019 study using the 2MRS survey found only mild underdensity, maybe 10 to 20% below average, not the 30 to 50% needed to explain the Hubble tension. A 2022 study using the DESI survey's early data found small-scale inhomogeneities, but no evidence for a giant supervoid extending billions of light years. The issue is complicated by selection effects. Galaxies in underdense regions might be systematically different, smaller, dimmer, making them harder to detect, which could create apparent underdensities that aren't real. Verdict: some surveys find evidence for local underdensity, but the magnitude and extent vary depending on which survey and analysis method you use. It's unclear if there's a large enough void to solve the Hubble tension. Chapter 14: The Copernican Principle and Cosmic Variance. Let's address the philosophical objection to the void hypothesis. Are we in a special location? The Copernican principle states that we don't occupy a privileged position in the universe. Earth isn't the center of the solar system. The sun isn't the center of the galaxy. Our galaxy isn't special. We're just typical. This principle has guided cosmology for centuries and has been validated repeatedly. When we look at the universe on large scales, it does appear homogeneous and isotropic. We don't seem to be in a special place. But the void hypothesis requires us to be in a somewhat special location, inside one of the largest underdense regions in the observable universe, located close enough to its center that our measurements are significantly biased. How unlikely is this? The statistics of cosmic variance. Even in a homogeneous universe, there will be regions that are randomly more or less dense than average. The question is, how unusual would it be to find ourselves in a void large enough to explain the Hubble tension? Several statisticians and cosmologists have calculated this. A 2020 paper by Kenworthy estimated that the probability of randomly being in a void as large and underdense as needed to solve the Hubble tension is roughly 1 in 100 to 1 in 1,000. Not impossible, but also not typical. If this is the explanation, we drew a fairly unusual cosmic lottery ticket. A 2023 study by Buchert and colleagues argued that we shouldn't be surprised by this. With billions of observers potentially existing in the universe, assuming life exists elsewhere, someone has to be in the unusual locations. The fact that we're the ones making the measurement means we're necessarily in a place where observers exist, which introduces selection bias. This is a variant of the anthropic principle. We observe what we observe partly because we exist, and our existence requires certain conditions that might not be typical. The counter-argument. Critics argue that invoking anthropic reasoning or accepting that we're in an unusual location is a slippery slope. Once you allow "we just happen to be in a special place" as an explanation, you can explain away any observation. Dark energy seems weird? Maybe we're in an unusual region where it's stronger. Galaxy formation doesn't match predictions? Maybe our local environment is atypical. Any anomaly becomes explainable by saying, "we're just in a weird spot." This doesn't lead to testable, falsifiable science. It's a retreat to "we got unlucky," instead of finding deeper explanations. The counter argument is that if the alternative is inventing entirely new physics, early dark energy, modified gravity, etc., with no independent evidence, maybe accepting that we're in a moderately unusual location is actually the more conservative option. Chapter 15: Alternative Void Models. Not all void models are created equal. There are several different ways to implement the "we're in a void" hypothesis with different predictions and requirements. The giant LTB void. This is the classic model, a spherically symmetric void, billions of light years across, with us near the center. Pros: mathematically clean and calculable, can be tuned to exactly match the Hubble tension. Cons: requires extreme fine-tuning of the void's properties. Should produce clear observational signatures that we don't convincingly see. Violates Copernican principle. The tilted void. What if the void isn't spherical but elongated, and we're not at the center but offset to one side? This model, proposed by several groups, suggests the void could be elongated in one direction, with us closer to one edge than the center, surrounded by denser structures like the Shapley supercluster pulling matter away. Songrui might better match the complex structure we actually observe. Could explain why we don't see perfect spherical symmetry in observations. Less extreme requirements on void size and underdensity. Cons: more parameters to tune, still requires us to be in a fairly unusual location, makes predictions harder to test because the geometry is more complex. The void network. Instead of one giant void, what if we're in a region of space with a higher than average density of voids? The cosmic web has a foamy structure. Some regions have lots of large voids clustered together. If we're in such a region, the average local density could be lower than the cosmic mean without requiring one impossibly large void. Pros: might be more consistent with what galaxy surveys show. Doesn't require one specific giant structure. Could be more consistent with the Copernican principle. Being in a region with many voids is less special than being at the center of one giant void. Cons: harder to model mathematically. Multiple smaller voids might not create a coherent effect on expansion measurements. Still requires our local region to be systematically underdense on large scales. The dynamic void. What if the void is actively evolving, with matter still flowing outward and the underdensity growing over time? This model suggests the void is younger and less relaxed than assumed in static models. The expansion rate in the void is changing. Different observations at different times might give different results. Pros: could explain why local measurements seem to be shifting over time. More realistic than assuming a static void. Might require less extreme underdensity if the dynamics create stronger effects. Cons: even harder to model accurately. Would require very specific void formation history. Not clear. This actually helps with the Hubble tension. Chapter 16. What about other tensions in cosmology? The Hubble tension isn't the only problem in cosmology. there are other discrepancies between observations and predictions. If the void hypothesis is correct, does it help with these other issues? The S8 tension. S8 measures the clumpiness of matter in the universe, how strong the gravitational clustering is on large scales. The Planck CMB measurement predicts a certain amount of clumpiness based on the early universe. But when we directly measure clumpiness using gravitational lensing and galaxy clustering in the late universe, we get a lower value. Matter appears slightly less clumpy than the CMB predicts. The discrepancy is about 2 to 3 sigma, less extreme than the Hubble tension, but still concerning. Could a void help? If we're in an underdense region, the local matter distribution would be less clumpy than the cosmic average. This could potentially explain why our measurements of S8 are lower than predicted. Several papers have explored this. A 2021 study by Ullman and colleagues found that accounting for local structure might reduce the S8 tension, but probably doesn't eliminate it entirely. A 2023 analysis suggested that the same supervoid that might explain the Hubble tension could contribute to the S8 tension, but the effects go in complicated directions and don't obviously solve both problems simultaneously. Verdict: the void hypothesis might help with the S8 tension, but it's not a clean solution to both problems at once. The lithium problem. The Big Bang should have produced specific amounts of hydrogen, helium, and lithium in the first few minutes of cosmic history. We can measure these abundances in ancient stars and gas clouds. Hydrogen and helium abundances match predictions beautifully. But lithium is a problem. We measure only about 1/3 as much lithium-7 as predicted. This has been a puzzle for decades. Could a void help? No. The lithium problem is about the early universe, and being in a void wouldn't change what happened in the first minutes after the Big Bang. This is a completely separate issue requiring a different solution. The age of the oldest stars. Some of the oldest globular clusters appear to contain stars that are older than the universe. This is obviously a problem. The ages are calculated using stellar evolution models and depend on the cluster's distance and chemical composition. Small errors in any of these could resolve the issue. But if we take the measurements at face value, some stars appear to be 13.5 to 14 billion years old, which is awkward if the universe is only 13.8 billion years old according to the Planck measurement. If the local Hubble constant measurement is correct and the universe is younger, 12.8 billion years, this makes the problem worse, not better. Could a void help? Not really. The void hypothesis doesn't change the universe's age in a way that helps here. The bottom line: the void hypothesis, if true, specifically addresses the Hubble tension and might help with the S8 tension. But it doesn't solve cosmology's other problems. We'd still need explanations for lithium, stellar ages, and other anomalies. This is actually evidence against the void hypothesis being the complete story. If one simple explanation solved multiple problems at once, that would be compelling. The fact that it only addresses one specific issue suggests we might be looking at the wrong solution. Part 5. The bigger picture. What this means for cosmology. Chapter 17. The crisis of precision cosmology. The Hubble tension represents a deeper problem in modern cosmology. We've entered the age of precision measurements. and our precisely measured values don't agree. For most of the 20th century, cosmology was a rough science. Measurements had huge uncertainties. The Hubble constant was known to within a factor of 2 at best. Debates centered on whether the universe was 10 billion or 20 billion years old. In that environment, small discrepancies didn't matter. The error bars were so large that everything was consistent within uncertainties. But starting in the tall 1990s with COBE, then WMAP, then Planck for the CMB, and the Hubble Space Telescope for local measurements, we entered precision cosmology. Error bars shrank dramatically. This was supposed to usher in a golden age where we knew cosmic parameters to exquisite precision and could test our models rigorously. Instead, we discovered that our different precise measurements disagree. This is actually how science progresses. Phase 1. Rough measurements with large uncertainties. Everything appears consistent because the error bars are huge. Phase 2. Improved measurements reveal discrepancies. Something is wrong with our model, or our measurements, or our assumptions. Phase 3. Either find the error/systematic and resolve the discrepancy, or discover new physics. We're currently in Phase 2. The Hubble tension is forcing us toward Phase 3, but we don't yet know which path we'll take. Chapter 18. What happens if we're not in a void? Let's consider the possibility that the void hypothesis is wrong or insufficient. What then? If local structure can't explain the Hubble tension, we're left with more radical options. Option 1. New physics in the dark sector. Maybe dark energy or dark matter behaves differently than we think. Early dark energy, a new component of dark energy that was important in the early universe but negligible today. This would affect the CMB, but not local measurements. Models have been proposed, but they're complicated and require fine-tuning. Dark energy would need to turn on, have significant effects, then turn off again, all without leaving obvious traces in other observations. Interacting. Dark energy. Dark energy that interacts with dark matter or ordinary matter in specific ways. This could change the expansion history in ways that affect different measurements differently. But constructing a model that works is extremely difficult. Decaying dark matter. Dark matter that slowly decays into other particles over cosmic time. This would inject energy into the universe and change the expansion rate. But decay rates need to be tuned precisely to solve the Hubble tension without conflicting with other observations. Option 2. Modified gravity. Maybe Einstein was almost right, but general relativity needs a small modification on cosmic scales. Several modified gravity theories exist. FR, gravity, scalar tensor theories, massive gravity, Galilean models. Some of these can be tuned to address the Hubble tension, but they face serious challenges. General relativity has passed every test in the solar system and with binary pulsars. Any modification needs to reduce to GR in these environments, while still creating different effects on cosmic scales. Most modified gravity theories create other observable effects, changes to gravitational lensing, different gravitational wave propagation, modified structure formation. These predictions often conflict with observations. So far, no modified gravity theory successfully solves the Hubble tension while passing all other tests. Option 3, beyond the standard model particle, physics, Maybe there are new particles or interactions we haven't discovered. Extra neutrino species, dark radiation, or other light particles in the early universe could affect the CMB in ways that change the inferred Hubble constant. The problem? We have tight constraints on extra radiation from the CMB itself and from Big Bang nucleosynthesis. There's very little room for new particles without conflicting with something else. Option 4, something fundamentally wrong with the standard cosmological model. Maybe lambda CDM is just wrong in some fundamental way we haven't identified. This is the most radical option. Lambda CDM successfully explains the CMB power spectrum, large-scale structure formation, supernova observations, baryon acoustic oscillations, gravitational lensing, galaxy clustering, and dozens of other observations. A new model would need to explain all of these successes while also solving the Hubble tension. That's an incredibly high bar. Option 5, we're missing some systematic error. Maybe. Despite all the checks, there's a subtle error in one of the measurements that multiple teams have missed. This becomes less likely every year as more independent checks confirm the tension. But it remains possible. The reality. We probably won't know the answer for several more years. We need better measurements with reduced uncertainties, independent methods to measure the Hubble constant, more detailed observations of local structure, more precise tests of general relativity, possibly new telescopes and experiments. Chapter 19, Future Observations that will help. Several upcoming observations and missions will shed light on the Hubble tension and the void hypothesis. The James Webb Space Telescope, JWST, can observe Cepheids in galaxies much farther away than Hubble could reach. This will extend the distance ladder to greater distances, reduce systematic uncertainties in Cepheid measurements, allow independent calibration of Type 1, a supernova. Initial JWST results published in 2023 to 2024 have confirmed the high Hubble constant values from the SH0ES team. The tension persists even with better data. The Vera Rubin Observatory. Starting in 2025, this ground-based telescope will survey the entire visible sky repeatedly, cataloging billions of galaxies and tens of millions of supernovae. This will provide better maps of large-scale structure, allow detailed tests of whether we're in a void, give thousands of supernova distance measurements, enable precision tests of cosmic expansion in different directions. Euclid. This ESA space mission, launched in 2023, is mapping the 3D distribution of galaxies over billions of light years. It will create the most detailed map of cosmic structure ever made, measure galaxy clustering and weak gravitational lensing, test whether local structure is unusual, provide independent measurements of cosmic expansion. The Nancy Grace Roman Space Telescope. Scheduled to launch in 2027, Roman will survey huge areas of sky with excellent sensitivity. It will discover thousands of Type 1, a supernovae, measure their distances precisely, test for systematic errors in supernova cosmology, map the 3D structure of the universe in unprecedented detail. Gravitational wave cosmology. LIGO and Virgo detect mergers of black holes and neutron stars. These collisions produce gravitational waves that can be used as standard sirens to measure cosmic distances independent of the distance ladder. With enough detections, gravitational waves could provide a completely independent measurement of the Hubble constant, breaking the deadlock between CMB and local measurements. Current results are consistent with either value within large uncertainties, but as more events are detected, the precision will improve dramatically. The Simons Observatory and CMB-S4, these next-generation CMB experiments, will map the microwave background with even better precision than Planck. They will reduce uncertainties in the CMB-derived Hubble constant, better characterize the ISW effect from large-scale structure, test for anomalies that might indicate new physics, measure subtle effects that could distinguish between competing models. Extremely large telescopes, the Extremely Large Telescope, ELT, the 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, will all come online in the late 20s and early 30s. These will measure distances to individual stars in distant galaxies, calibrate the distance ladder with unprecedented precision, study the properties of Cepheids and other standard candles in exquisite detail, test for evolution in stellar properties over cosmic time. Chapter 20. The philosophical implications. Beyond the technical details, the Hubble tension and the void hypothesis raise profound questions about how we do science and what we can know about the universe. The problem of local measurements. All of our observations are made from one location, Earth. We can't get an outside view of the universe. Everything we measure is filtered through our local environment. If we are in an unusual region, a large void, or any other atypical structure, how would we know? We can't go outside and look back in to check. This is fundamental limitation of cosmology. We have only one universe to observe, and we can only observe it from one location, or rather, one small volume as we look outward from Earth. This means there's always some irreducible uncertainty about whether our measurements represent the universe as a whole or just our local environment. The tension between simplicity and reality. The cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales, is incredibly useful. It makes cosmology tractable. We can write down simple equations and make testable predictions. But what if reality is messier? What if the universe is homogeneous on very large scales, but has significant structure on intermediate scales that affects our measurements? The void hypothesis suggests we might need to give up some simplicity to match reality. We might need models that account for local inhomogeneities, even if it makes the mathematics harder. Science often progresses by starting with simple models and adding complexity as needed. Maybe we're at that point in cosmology. The question of specialness. Are we special? It's a question humans have asked throughout history, and the answer has consistently been no. We're not the center of the solar system. Our planet isn't unique. The sun is an ordinary star. Our galaxy is one of billions. Even our supercluster isn't remarkable. The void hypothesis would make us somewhat special again, not cosmically unique, but in a notable location. One of the relatively few observers in a very large void. Should this bother us? Is it evidence against the hypothesis? Or is it just a statistical fact that someone has to be in the unusual locations, and it happens to be us? There's no objective answer. It's a matter of scientific philosophy and how we weigh different types of evidence. The nature of scientific progress. The Hubble tension illustrates how science advances. We don't always move smoothly from ignorance to knowledge. Sometimes better measurements create new mysteries rather than resolving old ones. This is frustrating, but also exciting. Mysteries drive science forward. The Hubble tension is forcing us to check our assumptions, test our models more rigorously, and consider new possibilities. Whether the solution is a void, new physics, or a subtle systematic error, we'll learn something important. Either we'll better understand our local cosmic environment, or we'll discover new fundamental physics, or we'll identify measurement techniques that need refinement. All of these are valuable outcomes. Part 6. Bringing it all together. Chapter 21. The current state of the void hypothesis. After examining all the evidence, where does the void hypothesis stand today? The case for one. There is evidence for local underdensity. Multiple studies find that our region of space has slightly fewer galaxies than the cosmic average. The magnitude and extent vary between studies, but the basic finding is robust. 2. Some observations show hints of expected signatures. There are marginal detections of CMB temperature decrements, anisotropic expansion, and peculiar velocity patterns that could be consistent with void effects. 3. It would solve the problem without new physics. If the void explanation works, we don't need to modify our cosmological model or invent new particles. We just need to account for our local environment. 4. Multiple independent analyses support it. The KBC Void has been found in different galaxy surveys using different methods. It's not a one-off result from a single team. 5. It's physically plausible. Voids exist. We know they affect local expansion. The question is just whether the effect is large enough, not whether it exists at all. The case against. 1. The void isn't extreme enough. Most surveys find local underdensity of 10 to 30%, not the 30 to 50% needed to fully explain the Hubble tension. 2. The void isn't large enough. To bias all our local measurements, the void would need to extend well beyond the distances to our standard candles. Most evidence suggests it doesn't. 3. Expected signatures aren't clearly detected. The CMB cold spot isn't in the right place. The anisotropy and expansion is marginal. The peculiar velocities don't show clear void outflow patterns. 4. It requires us to be in a special location. While not impossible, it requires accepting that we're in one of the largest voids in the observable universe, close to its center. 5. It doesn't fully solve the problem. Even optimistic void models account for maybe 2 to 3 kilometers per second per megaparsec of the tension, not the full 5.8 kilometers per second per megaparsec discrepancy. The consensus view, most cosmologists think, we probably are in a mildly underdense region. This might contribute to the Hubble tension, but it's not the complete explanation. We still need something else, either new physics or a systematic error, or both. In other words, the void hypothesis is part of the story, but not the whole story. Chapter 22. What this means for you. Why should anyone care about the Hubble tension, or whether we're in a void? On a practical level, it doesn't affect your daily life. The expansion rate of the universe has no bearing on your morning coffee or your commute to work. But on a deeper level, this matters because it's about understanding our place in the cosmos. We're part of the universe. The atoms in your body were forged in stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, all created in stellar furnaces and scattered through space when those stars died? You are literally made of star stuff, as Carl Sagan famously said. Understanding the universe is understanding yourself. It affects how we think about reality. Are we in a typical location in a homogeneous universe? Or are we in an unusual bubble within a more complex cosmos? The answer shapes how we think about cosmic history, the formation of galaxies and stars, and ultimately the emergence of life. If we're in a void, it might be relevant to the conditions that allowed our solar system and Earth to form. Voids have different environments than dense regions. Matter behaves differently. Star formation happens at different rates. Maybe being in a void is part of what made our existence possible. Or maybe it's just a coincidence and life would arise regardless. It's about intellectual honesty. Science is the process of trying to figure out what's actually true, even when the truth is complicated or uncomfortable. The Hubble tension represents science working as it should. We have contradictory measurements. We don't know the answer yet. So we're checking our work carefully, considering multiple explanations, gathering more data, debating interpretations, slowly converging on the truth. This is how knowledge advances, messy, uncertain, full of debate and disagreement, but always grounded in evidence and observation. It inspires wonder. The universe is vast and strange. We live in a cosmos where space itself expands, where dark energy pushes galaxies apart, where structures billions of light years across form and evolve over billions of years. We might live in a cosmic bubble where the local expansion rate is different from the universal average, or we might not. Either way, the fact that we can ask these questions and design observations to answer them is remarkable. 50 years ago, we barely knew the universe was expanding. Now we're arguing about whether local inhomogeneities bias our expansion measurements by 9%. That's incredible progress. Extended Part 7: The Deeper Implications and Cutting-Edge Research. Chapter 23: The Multi-Messenger Approach to Cosmic Expansion. One of the most exciting developments in addressing the Hubble tension is the emergence of completely independent ways to measure cosmic expansion. These methods don't rely on the traditional distance ladder or the CMB, offering fresh perspectives on the problem. Gravitational wave standard sirens. When two massive objects like neutron stars or black holes spiral into each other and merge, they produce gravitational waves, ripples in space-time itself, that propagate outward at the speed of light. LIGO, Virgo, and now Kagra detect these waves. And here's the incredible part. The gravitational wave signal itself tells us the distance to the merger. How? The amplitude, strength of the gravitational waves depends on two things: how massive the merging objects are and how far away they are. By analyzing the wave pattern, we can figure out the masses. Once we know the masses, we can calculate the intrinsic amplitude the waves should have. Comparing this to the observed amplitude tells us the distance. Meanwhile, if we can identify the host galaxy of the merger using electromagnetic telescopes, we can measure its redshift, how fast it's moving away from us due to cosmic expansion. Distance plus recession velocity equals Hubble constant. No distance ladder required, no CMB modeling needed. The first measurements. In 2017, LIGO and Virgo detected gravitational waves from a neutron star merger designated GW 170817. Within seconds, telescopes around the world spotted the corresponding explosion, a kilonova, in the galaxy NGC 4993. This was the first standard siren measurement of the Hubble constant. The result? H0 equals 70 kilometers per second per megaparsec, with a large uncertainty of about plus or minus 12. Not precise enough to resolve the tension, but right in the middle of the two competing values. Intriguing. Since then, more neutron star mergers have been detected, though not all have electromagnetic counterparts we can identify. Each detection slightly improves the measurement. A 2021 combined analysis of multiple events gave H0 equals 68 kilometers per second per megaparsec, with uncertainty plus or minus 5. Still not precise enough to definitively favor one side, but trending toward the lower CMB value. However, there are complications. The gravitational wave measurement depends on correctly identifying the host galaxy, not always obvious. Understanding the viewing angle of the merger, we see different signal strengths from different angles. Modeling the merger physics accurately. The future, as more gravitational wave detectors come online, and existing ones improve sensitivity, will detect more mergers. Within a decade, we might have hundreds of standard siren measurements, giving us a precision comparable to current methods. This could break the deadlock. If gravitational waves consistently give H0 equals 73, it supports the local measurements and suggests the CMB modeling is wrong. If they give 67, it supports the CMB and suggests systematic errors in the distance ladder. If they give something in between, well, that would be even more confusing and might support the void hypothesis or point to even stranger physics. Surface brightness. Fluctuations. Here's another independent method that's gaining traction. Measuring distances to galaxies using the statistical properties of their starlight. Galaxies are made of billions of stars. When you look at a distant galaxy, you can't see individual stars. They blend together into a smooth glow. But the glow isn't perfectly smooth. There are tiny fluctuations in brightness from pixel to pixel in an image, caused by the random distribution of stars. The amplitude of these fluctuations depends on distance. In a nearby galaxy, the fluctuations are larger because you're resolving the light into smaller regions containing fewer stars each. In a distant galaxy, the fluctuations are smaller because each pixel contains light from more stars averaged together. By measuring these fluctuations carefully, you can determine distance. Recent results. A 2024 study by Blakesley and colleagues used surface brightness fluctuations to measure distances to galaxies out to about 100 million light-years. Combined with velocity measurements, they calculated H0 equals 73.3 kilometers per second per megaparsec. This agrees with the SH0ES distance ladder result and disagrees with the CMB value. Importantly, surface brightness fluctuations are completely independent of Cepheids and supernovae. They don't use the same calibrators or assumptions, yet they get the same answer as the distance ladder. This is strong evidence that the high Hubble constant value is real and not caused by some systematic error specific to Cepheids or supernovae. Tip of the red giant branch? Yet another independent method involves old evolved stars called red giants. As stars age and exhaust their hydrogen fuel, they swell up and cool down, becoming red giants. Eventually, they reach a maximum brightness, the tip of the red giant branch, before undergoing helium fusion in their cores. This maximum brightness is remarkably consistent from star to star, making it another standard candle. The advantage over Cepheids. Red giants are more common and can be seen in older stellar populations, giving us access to different types of galaxies. Recent results. Multiple teams have used TRGB measurements from Hubble and now JWST. The results consistently give H0 around 72 to 73 kilometers per second per megaparsec. Again, independent of the distance ladder, yet agreeing with it. The pattern. Are you seeing the pattern? Every local measurement method, distance ladder with Cepheids, gravitational waves, surface brightness fluctuations, tip of the red giant branch, trends toward higher values around 73. Methods based on the early universe, primarily the CMB, give lower values around 67. It's not one method versus another. It's local versus global, late universe versus early universe. This pattern is exactly what you'd expect if we're in a region where expansion is genuinely faster than the cosmic average. But it's also what you'd expect if there's new physics that affects the early and late universe differently. Chapter 24. The Timescape Cosmology. Alternative. Let me introduce you to one of the more radical alternatives to both the void hypothesis and standard new physics proposals. Timescape Cosmology. Developed primarily by David Wiltshire at the University of Canterbury in New Zealand, Timescape takes seriously the fact that space isn't homogeneous and that this should affect how we think about cosmic expansion. The core idea. In standard cosmology, we treat the universe as smooth and homogeneous on large scales. Yes, there are galaxies and voids, but we assume we can average over these and treat the cosmos as a uniform fluid. Timescape says, what if this averaging is wrong? What if the presence of structure fundamentally changes cosmic evolution in ways we're not accounting for? Here's the key insight. General relativity tells us that time flows at different rates in regions with different gravitational potentials. Near a massive object, time runs slower. In empty space, far from any mass, time runs faster. On Earth, this effect is tiny and only matters for GPS satellites and precision experiments. But on cosmic scales, in a universe with massive galaxy clusters and vast empty voids, the effect might accumulate to something significant. The implications. Timescape proposes that time flows faster in voids than in dense regions. Because most volume is in voids, most of space-time is aging faster. This affects how we interpret cosmic expansion. When we observe distant galaxies and measure redshift, we're seeing light that has traveled through regions with different time flow rates. If we don't account for this properly, we might misinterpret the expansion history. Wiltshire argues that timescape can explain the Hubble tension without requiring dark energy at all. The apparent acceleration of cosmic expansion might be a consequence of inhomogeneous time flow rather than a mysterious energy component. The evidence. Timescape makes different predictions than standard cosmology for various observations. Supernovae. Timescape predicts a specific relationship between distance and redshift that differs from lambda CDM. Some analyses suggest supernova data fits timescape as well as or better than standard cosmology. BAO, baryon acoustic oscillations, the characteristic scale of density. Fluctuations from the early universe should appear at different scales in timescape versus lambda CDM. Some studies find better fits with timescape. The CMB. This is trickier. Timescape predicts the CMB should look somewhat different than in standard cosmology. Whether it matches observations better or worse is debated. The Hubble tension. Timescape naturally produces different expansion rates in different regions based on local density, potentially explaining why local and global measurements disagree. The controversies. Timescape is controversial for several reasons. Complexity. The mathematics is significantly more complex than standard cosmology. This makes it harder to calculate predictions and test the model. Unfamiliarity. Most cosmologists are trained in standard perturbation theory and lambda CDM models. Timescape requires a different conceptual framework that's harder to work with. Alternative explanations. Many of Timescape's successes might be explainable within standard cosmology with tweaks rather than requiring a complete rethinking. Testability. Some critics argue Timescape's predictions are flexible enough that it can fit almost any data, making it less scientifically useful. The verdict? Timescape remains a minority view in cosmology, but it's not fringe pseudoscience. It's published in peer-reviewed journals, taken seriously by at least some researchers, and continues to make testable predictions. Whether it's correct or not, it illustrates an important point. The Hubble tension might require us to rethink fundamental assumptions about cosmic expansion, not just add a new particle or field to our model. Chapter 25. What we can learn from simulations. Computer simulations of cosmic structure formation have become incredibly sophisticated. They can model billions of particles over cosmic volumes, tracking how matter clusters under gravity from the early universe to the present day. Can these simulations help us understand the Hubble tension and test the void hypothesis? The Millennium Simulation and its descendants. Projects like the Millennium Simulation, Illustris, Eagle, and most recently Illustris TNG have created virtual universes with stunning realism. They include dark matter, gravitational clustering, gas dynamics and hydrodynamics, star formation, supernova feedback, black hole growth and feedback, sometimes even magnetic fields and cosmic rays. These simulations reproduce the observed cosmic web structure remarkably well. Filaments, walls, clusters, and voids that look like what we see in galaxy surveys. Testing the void. Hypothesis in simulations. Researchers can use these simulations to test whether voids like the hypothetical KBC supervoid are statistically likely. How common are voids of that size and under density? If they're extremely rare, the void hypothesis becomes less plausible. Effectively biasing measurements. If you place a virtual observer in a simulated void and have them measure the expansion rate using simulated Cepheids and supernovae, do they get a biased result? Observable. Do simulated voids produce the signatures we should see in the CMB galaxy distributions and peculiar velocities? Key findings from simulations. A 2020 study by Kenworthy and colleagues placed virtual observers at random locations in the Millennium Simulation and had them measure the local Hubble constant. They found significant scatter in measurements depending on location. About 68% of observers measured values within 2% of the true value, but about 5% of observers were biased by more than 5%. The largest biases occurred for observers near the centers of the largest voids. This suggests that being in a void can bias measurements, but you need to be in a particularly large void and located in just the right spot. Another 2023 study using Illustris TNG found that to produce a 9% bias in the Hubble constant, you need a void at least 1.5 billion light-years in radius, underdensity of at least 40%, observer location within 300 million light-years of the center. These requirements are right at the edge of what's plausible, but not impossible. The simulation limitations. Simulations have limitations. Resolution. Even the largest simulations can't resolve everything. Small-scale physics might affect how voids form and evolve in ways simulations miss. Physics assumptions. Simulations build in assumptions about dark matter, dark energy, and other physics. If those assumptions are wrong, the simulations might not reflect reality. Box size. Simulations have finite volumes. The largest structures might not fit properly, or their behavior might be affected by the simulation boundaries. Initial conditions. Simulations start from specific initial conditions. Maybe our universe happened to form voids in a slightly different way than typical simulations produce. Still, simulations provide valuable insights. They tell us that the void hypothesis is plausible, but requires specific, somewhat unlikely conditions. They're not a smoking gun for or against the idea. Chapter 26. The anthropic question. Should we even be surprised? Let's wade into controversial philosophical waters. The anthropic principle and what it means for the Hubble tension. The weak anthropic principle states, we observe the universe to have properties compatible with our existence because if it didn't, we wouldn't be here to observe it. This is tautologically true, but not very useful. The stronger version suggests the universe must have properties compatible with the emergence of observers, and this constrains what we should expect to measure. This gets more controversial. Applied to the Hubble tension. If we're in a void, we might ask, is being in a void somehow necessary for our existence? This seems far-fetched at first. Why would galaxy formation, planet formation, or the origin of life depend on being in an underdense region? But maybe there are subtle connections, star formation rates. Voids have lower star formation rates than dense regions. Maybe intermediate density environments, like the edges of voids, have optimal conditions for forming long-lived stable stars like our Sun. Heavy element production. The chemical elements necessary for life, carbon, oxygen, nitrogen, etc., are produced in stars and distributed by supernovae. The rate and pattern of element enrichment might vary between voids and dense regions. Galactic dynamics. The Milky Way's structure and stability might be influenced by its environment. Being in a void could affect tidal interactions, merger rates, and other factors that influence galactic evolution. Planetary system formation. The frequency of planetary systems might depend on metallicity, abundance of heavy elements, which varies with environment. Void environments might have different planetary system demographics. These connections are extremely speculative. We have no strong evidence that being in a void is necessary for life. But the anthropic principle reminds us, if there are millions of observers in the universe, and only those in certain environments can measure the Hubble constant precisely, because they develop advanced civilizations and technology, then those measurements will be systematically biased by the environments where complex life arises. The criticism. Most physicists are uncomfortable with strong anthropic reasoning because it's unfalsifiable. You can explain anything by saying, "We observe this because we must be in a location where observers can exist." It gives up on deeper explanations. Instead of finding physical reasons, you appeal to observer selection. It might be unnecessary. Maybe the void hypothesis is wrong, and the real explanation is new physics that has nothing to do with our location. The defense. Proponents argue it's a selection effect. Just like how we shouldn't be surprised that we evolved on a planet in the habitable zone because life requires liquid water, we shouldn't be surprised if we're in a region with properties conducive to complex structure formation. It makes predictions. If being in a void is typical for observers, we should expect other intelligent civilizations, if they exist, to also be in voids, which might affect SETI strategies. It's scientifically legitimate. Astronomy routinely deals with selection effects. The anthropic principle is just another form of selection bias. The bottom line. Whether or not anthropic reasoning is useful, it raises an important point. We should be cautious about assuming we're in a typical location just because the Copernican principle says we shouldn't be special. If there are physical reasons why observers tend to arise in certain environments, then observers will systematically be in those environments, and measurements made by observers will be systematically biased. This doesn't prove we're in a void, but it suggests we should take the possibility seriously, even if it requires us to be in a somewhat unusual location. Chapter 27. The Economic and Societal Impact of Cosmological Research. You might wonder, why do we spend billions of dollars on telescopes and experiments to resolve the Hubble tension? Does it really matter whether the expansion rate is 67 or 73? The direct economic impact. Cosmological research employs thousands of people. Astronomers and physicists, engineers designing instruments, software developers creating analysis tools, technicians maintaining telescopes, support staff at observatories and universities. Major projects like JWST, Vera Rubin Observatory, and Euclid cost billions, but create thousands of high-skilled jobs. The technology developed for these projects often has spin-off applications. CCD sensors developed for astronomy are now in digital cameras and medical imaging. Data analysis techniques from cosmology are used in machine learning and AI. Precision optics from telescopes improve everything from microscopes to laser surgery. Cryogenic technology from infrared detectors has applications in quantum computing. The educational impact. Cosmology captures public imagination and inspires students to pursue STEM careers. How many physicists, engineers, and computer scientists chose their careers because they were fascinated by questions about the universe? The Hubble tension, with its mysterious discrepancy and competing explanations, is exactly the kind of puzzle that excites young minds and draws them into science. The philosophical and cultural impact. Understanding our cosmic context matters for how we see ourselves and our place in nature. Are we in a typical location in a homogeneous universe? This supports the Copernican principle and suggests that what we observe is representative of the cosmos as a whole. Or are we in an unusual void? This makes us slightly special and reminds us that our observations might not represent the full picture. These different worldviews, while not affecting daily life, influence how we think about the uniqueness or typicality of Earth and life, the likelihood of other civilizations existing elsewhere, the long-term fate of the universe and humanity's place in it, the nature of scientific knowledge and what we can learn from one observation point, the case for fundamental research. The Hubble tension research won't cure cancer or solve climate change, but it represents humanity's effort to understand reality at the deepest level. History shows that fundamental research often produces unexpected practical benefits decades later. Einstein's general relativity seemed purely theoretical in 1915, but GPS satellites rely on it today. Quantum mechanics seemed like esoteric physics in the 1920s, but now underpins semiconductors, lasers, and modern technology. Nuclear physics seemed academic, but led to nuclear energy and medical isotopes. We can't predict what technologies might emerge from better understanding dark energy, cosmic expansion, or the large-scale structure of the universe. But history suggests there will be applications we can't currently imagine. Moreover, there's intrinsic value in knowledge. Understanding the universe is worth doing for its own sake, as an expression of human curiosity and intellectual achievement. Chapter 28: How You Can Follow the Story. The Hubble tension is an ongoing scientific detective story with new clues emerging regularly. If you want to follow along, academic papers. The Arxiv preprint server, arxiv.org, publishes physics and astronomy papers before peer review. Search for Hubble tension and you'll find the latest research. Key journals include the Astrophysical Journal, monthly notices of the Royal Astronomical Society, Physical Review, D, Nature and Science, for major breakthroughs, conference talks. Major astronomy and physics conferences often post talks online. American Astronomical Society meetings, International Astronomical Union symposia, Cosmology from Home, online conference series. Science communication. Several physicists and astronomers actively communicate this research. Adam Rees, SH0ES team leader, sometimes gives public lectures. Various YouTube channels cover cosmology news. Podcasts like Daniel and Jorge Explain the Universe and Star Talk occasionally discuss the Hubble tension upcoming milestones to watch. 2025. First Vera Rubin Observatory data releases providing detailed maps of cosmic structure 2026 to 2027. More JWST, Cepheid measurements extending the distance ladder 2027. Nancy Grace Roman Space Telescope launch, beginning major supernova survey 2028 to 2030. Accumulated gravitational wave standard siren measurements should reach competitive precision in 2030 plus. Next generation CMB experiments, Simons Observatory, CMBS4, will refine early universe measurements. By 2035, we should have a resolution. We'll know whether we're in a void, whether there's new physics, or whether someone found a systematic error everyone missed. Final extended conclusion. We've journeyed through one of the most perplexing mysteries in modern cosmology. The Hubble tension, a 9% discrepancy in measurements of cosmic expansion, has challenged our understanding of the universe and forced us to question assumptions we thought were solid. The void hypothesis offers an elegant possible solution. Maybe we're located in an unusually large, underdense region where space expands slightly faster than the cosmic average. This would explain why local measurements give higher expansion rates than global measurements based on the cosmic microwave background. But as we've seen, the evidence is mixed. Supporting the void idea? Multiple surveys find local underdensity. Some observations show expected void signatures. Simulations confirm voids can bias measurements. It requires no new physics, just accounting for our location. Challenging the void idea? The underdensity isn't extreme enough in most surveys. Key signatures like the CMB cold spot aren't clearly detected. It requires us to be in a somewhat special location. It probably can't explain the full tension. The truth might be somewhere in between. Perhaps we're in a moderately underdense region that accounts for part of the Hubble tension, with the rest explained by subtle new physics or small systematic errors. What we've learned. This investigation teaches us several important lessons about modern science. Precision reveals complexity. Better measurements don't always give clearer answers. Sometimes they reveal that nature is more complicated than our models assumed. Local versus global matters. Where you make a measurement affects what you measure. Our location in the cosmic web might bias our observations in ways we're only beginning to understand. Independent verification is crucial. The fact that multiple independent methods give similar results, local methods around 73, CMB methods around 67, suggests both are measuring something real, even if we don't fully understand what. Humility is warranted. We've mapped the cosmic microwave background, cataloged billions of galaxies, and launched telescopes to observe the universe with unprecedented precision. Yet we still can't agree on a basic parameter like the expansion rate. The cosmos still holds mysteries. The path forward, the next decade, will be transformative. New telescopes and instruments will provide data of unprecedented quality and quantity. Gravitational wave observations will offer completely independent expansion measurements. Detailed maps of cosmic structure will reveal whether we're truly in an unusual region. We'll either 1. Confirm we're in a large void and revise our understanding of how location biases observations 2. Discover new physics, early dark energy, modified gravity, or something even more exotic 3. Find a subtle systematic error that explains the discrepancy 4. Learn that the answer is some combination of these factors. Any of these outcomes will advance our understanding. Science wins regardless of which explanation proves correct. A personal reflection. There's something profound about standing on a small planet, looking out at the cosmos, and asking, how fast is space expanding? The fact that we can ask this question and design observations to answer it is remarkable. The fact that the answer is complicated and uncertain doesn't diminish the achievement. It enhances it. We're doing science at the frontier of knowledge, where certainty gives way to mystery and exploration. The Hubble tension represents the cutting edge of cosmology, where our best models meet observations that don't quite fit. This is where the most interesting science happens. This is where paradigms shift and understanding deepens. Whether we're in a cosmic hole or not, whether the universe's expansion rate is 67 or 73 or something else entirely, the journey to find out is advancing human knowledge in profound ways. We're mapping the universe, testing fundamental physics, and learning about our cosmic context. We're developing new technologies, training new generations of scientists, and inspiring wonder about the cosmos. That's worth celebrating, even if we don't have all the answers yet. The universe doesn't care. The universe is what it is, regardless of our theories or preferences. Space expands at whatever rate it expands. We might be in a void, or we might not. Our models and measurements are just our attempts to understand reality. When they disagree, it's not the universe that's wrong. It's our understanding. The Hubble tension is humbling. It reminds us that despite all our sophisticated instruments and elegant theories, we're still trying to figure out basic facts about the cosmos. But it's also exciting. Every mystery is an opportunity to learn something new, to push the boundaries of knowledge, to discover aspects of reality we never suspected. Final thoughts. Are we in a cosmic hole? The evidence suggests we're probably in a somewhat underdense region, though maybe not extreme enough to fully explain the Hubble tension on its own. Does this solve the crisis in cosmology? Probably not completely, but it might be part of the solution. Will we know for certain within a decade? Almost definitely. The observations coming online in the next 10 years will settle this question one way or another. Until then, the Hubble tension remains one of the most fascinating unsolved problems in physics. It's a reminder that the universe still has the capacity to surprise us, to challenge our assumptions, and to reveal layers of complexity we didn't anticipate. And honestly, that's exactly how it should be. The cosmos is vast, ancient, and strange. We're here for a brief moment, trying to understand it with our limited perspective and imperfect instruments. The fact that we've learned as much as we have is extraordinary. The fact that mysteries remain is what keeps science vital and exciting. So whether we're in a cosmic hole or not, we're definitely in an incredible era of cosmological discovery. And the best is yet to come. Keep looking up. Keep asking questions. And stay curious about the universe that surrounds us all. The answers are out there, waiting to be discovered.